This is what I'm after. This is what I'm after, something like this. But what I'm trying to do is I'm trying to generalize, right? I'm trying to see if it's not just true in the case we just looked at, but always true. Mathematicians are always after this kind of thing, right? It's called abstraction. You get rid of concrete numbers and figure out what's true all the time, no matter what numbers you throw at it. Okay? So you remember how we began? We began with x double dot, and then I supplied a number. As soon as I supplied a number, it became a specific situation. But I want it to be true all the time. Right? So I'm going to come back to this guy. Okay? So that's all I'm establishing, right? And the way I made progress from here to something like this was I put it together with this. This is what my heading is, right? Okay. So, in other words, we're looking at acceleration. We're looking at it from two different angles, okay? What are we going to get? Well, let's try doing this approach, what we did before, but doing it in general terms. What's going to happen? Okay, what have I got? I've got this is equal to this. Is that all right? So far, so good. Still got my equations in terms of x, so I'll integrate. And you'll get this. Does that check out? Just integrated, no problems. Okay. Now, I'm getting towards something like this, aren't I? I'm getting there, okay? But I've got two problems. Number one, it's not in terms of v². Number two, I've still got this constant flying around, right? Well, hold on a second. Let's get rid of the half. That's not hard to do. Okay. How did we get rid of the constant last time? We had an initial condition, right? I'm not giving you any conditions. I'm giving you nothing. It can be any kind of simple harmonic motion, okay? But this constant can't be anything, right? I can still work out what this is, okay? Now, it's a bit tricky. You said to me initial conditions, but actually, we didn't end up using initial conditions here to get to this. Do you remember? We didn't actually need to know about time. What did we need to know? Yeah, we needed a relationship between displacement and velocity. There's no time there. So I don't care if it's initial or not, okay? So you've got a couple of ways to approach this. A couple of ways, right? For instance, you can say, look, about this motion, okay? I don't know, well, all I know basically is that it's got the center of motion being the origin. It's basically all I know, okay? But that gives me some information. For instance, when I'm at the origin, in theory, I should actually know how fast I'm going. Shouldn't I? That's when I'm going fastest. Okay? Now I know we don't know what any of the numbers are. We don't know what amplitude is. We don't know what period is, but I can still work it out. Alternatively, I should be able to say at the extremities, the amplitude, right? At either of the extremities, I should know the velocity, right? What will the velocity be? It'll be 0, right? This is actually the situation we got before, except they just told us one of the examples, okay? An instance of that, right? Now you can go at this, sorry. What you'll find is that you'll have this velocity, okay? It's not that hard to determine. Think about it. I'm gonna go with this. The numbers are a little bit simpler. Watch what happens, okay? I'm gonna substitute that in here. Because everything's being squared, it doesn't matter whether you take the positive or negative. I'm just going to take the positive anyway. Okay. When I'm at the positive extremity, I have velocity 0. Okay. So in he goes. Let's see. 0 equals. You happy with that? Is that okay? I just subbed it in. So now I have 2c. 2c is just a squared n squared. So I can bring this back into this equation. Minus n squared x squared. Can you see it emerging? There you go. Take your factor out. Did I take the factor out? Nope, sorry. Not that one. I actually had it here, didn't I? There you go. So there's your proof that this is not just a coincidence. It is actually true all the time. V squared. Okay. Alternatively, you could have gone this way. Do you want to see it? It doesn't take very long. Watch. Instead, I'll take the origin as my point of reference. By the way, what does this tell you? The more frequent the graph is, and the higher it has to go, the faster it's coming back through the origin, past the origin, I guess. Okay, because, think about this. If I have this graph, and I increase the amplitude, right, like this. Okay, obviously, he's coming back faster, past the origin. In the same way, if I think about this guy, and I increase the frequency to something like this. Again, he's coming back faster across the origin, right? So these are your two factors that affect your velocity past the origin. Where am I? Here's the equation I'm subbing into. Okay, so v equals an, that's the left-hand side, equals 0 squared plus 2c. Oh, surprise! Look, you get the same constant, and back you'll go. Okay, so I could have taken either of these reference points, and they would have supplied me with the same result at the end. Okay, you cannot quote this result. You cannot quote it. You have to arrive at it in much the same way that we have, except you'll have numbers in its place. Okay. However, because it started from this point, what it means is this is an independent way of verifying that something is simple harmonic motion. Okay. If you see this, you're like tick. That means it's simple harmonic motion, right? If you see this in exactly the same way, you can say, well, it came from there. These are parallel results. They're just looking at it from another angle. Okay. So it's another way to verify it. Okay.